Let's get started. Thanks for coming. I am Patrik Sundberg. I am a software engineer at Google, where I work in healthcare and machine learning for healthcare in general. And I'm going to talk today a little bit about some of the technology that's underpinning some of the stuff that Eyal showed earlier in his keynote, and that you've seen maybe in some of the publications that we've had, and just talk a little bit in general about how we approach working with large data sets and complicated data sets like data sets in healthcare. And so a lot of this talk is going to be centered on the open source repository that we put out earlier this year that is going to have an increasing amount of tools of the type of things that we use internally that we're able to share. And so the top level message of this talk is we really want to have a conversation with you about what would be useful for the community. And so we encourage you to go and see what's already on GitHub. I'll talk a little bit more about what's about to come. But if you try it out, see if it's useful for you. If it's not, what would be useful. We appreciate feedback. And as I said, the contents will grow over time. All right, so the talk here is titled FHIR and Protocol Buffers. And so hopefully by the end of the talk you'll have a better understanding of what protocol buffers are. But I do want to sort of emphasize that this is just one of many tools that we use, and it is important because it's sort of the foundation of a lot of other things that we do, like queries over data or data flow, and just moving data around. It gives us a way of working with it in a structured, working with data across languages in a structured representation. So I'll start by talking a little bit about protocol buffers in general, not healthcare specific, and then go back a little bit and loop around to why we're interested in it. And so this is, how many people are familiar with protocol buffers before? How many people have worked with them? All right, so a fair number of people. That's good. And so at a high level, the way you start working with protocol buffers is you want to represent some data. And so you define in the protocol buffer language a message, basically a data structure that can use a certain set of primitive types. So here, for example, we're defining a person. The person has a name, there's an ID, there's an email, there's a phone number, and there's various types of phone numbers that are allowed, and so we can have enums to sort of say that these are the allowed types. And then the fields can be either optional or repeated. So the phone number, you can have multiple phone numbers, for example. And so what you do is you start out by sort of defining your data in this way. And there's other ways approaches of doing similar things. But one thing I want to point out here is the equals 1, equals 2, equals 3 that you see at the end, which is probably a little confusing if you've never seen this before. These are the tag numbers for the protocol messages, and they are used to serialize the messages to disk and on wire. And so you actually do a little bit of work here specifying a unique number for each field, and they're used later when the messages are serialized. And so the next step that happens is once you've defined this, there's a protocol buffer compiler. And so this compiler will take this definition and it will turn it into code for many, many different languages, right? So here is a version of what might happen in Java, right? So from the definition you saw on the previous page with the name and the ID and email, now we get a bunch of methods, right? And so we can just call these methods. And if we change the definition of the message, then we will auto-generate again this code, and then the rest of your software that links to this, uses this, will be able to pick up the changes. And the nice thing is you get a lot of languages for free. So you make this definition only once. And so here is 4 different languages, see if you can spot which ones they are, that use the generated code that came from that specific message. So for example, the Java in the top left is essentially creating a new person. They're all doing the same thing, right? So creating the person, giving an ID, a name, an email, and then actually writing it to a file. And so the other little snippets use essentially the same data structure. And if you serialize this to disk, let's see. I should just mention that there's a lot of languages that are supported. So some on the left-hand side are more of the primary supported languages like C, Java, Python, Go. And then there's a lot of third-party contributions for other languages. So chances are that whichever language you're using, there is an implementation of protocol buffers that you can use. And so I want to come back to this serialization, the tag numbers that you saw earlier, which is used to, in a very efficient way, make a binary string out of an instance of your data, right? So typically, for example, the name, in this case, name equals 1, that was the tag number. That'll be 1 byte on the wire to say, hey, the name is about to come, and then there's a string that's the name, and so forth with IDs and other things, right? And this, to parse this, obviously special purpose code is needed, but that is also auto-generated for you by the protocol buffer compiler, so you never have to worry about that. And that means that if you have a system that involves servers, for example, that run in different languages, you might have some in C++, maybe something in Go, maybe something in Java. They can all communicate using the same messages. And if you change the message, you don't have to make sure that you keep them all in sync across all the languages. You just have to recompile, and then they'll pick up the changes. All right, so let's go back a little bit more about what we started out doing in the healthcare space here for Google. So we wanted to essentially look at de-identified medical records and try to make various types of predictions. And so the engine that we use to make predictions, the machine learning engine, is called TensorFlow. And so actually, how many people are familiar with TensorFlow? Okay, so a little more than the Protobuf. So this is another open source package on GitHub that is very popular, very frequently used. And it has a lot of powerful tools to help you use state-of-the-art machine learning techniques on your data. And we use the exact same thing internally and externally. And so the first thing that we wanted to do is we wanted to take this data and we wanted to put it in a format which was suitable for learning and working with it in TensorFlow. But as you can see, like this is just a very simple visualization of how complicated the data is. And you've seen this slide before. It is not as simple as one might hope and think before actually seeing real healthcare data. And in addition, every single healthcare institution that we work with have their own representation of the data. The tables, even if people use the same EHR vendors, the data warehouses, the tweaks that they do, and everything is a little bit different. So you can never really just start from there. You have to normalize in some way. And so we decided pretty early on to use FHIR for the representation to normalize the data, but there's more to it than that, right? So then the picture is essentially something like this. You start out with a bunch of different resources, you put it into FHIR, and then from FHIR we go to TensorFlow. So this is basically the model that we're following. But there's more to it, as I said, right? So if you have a data model, that's great, but how are you going to deal with the bytes? So FHIR defines a way of serializing to JSON, to XML. I feel like more people use the JSON representation these days than XML, but they are, in theory, both options that are well understood and documented, but maybe not as suitable for large data. So in our case, a lot of the work is going to be mapping the data from its raw format into FHIR. And that means that we're going to have to do this many, many, many times, because we're not going to get it right the first time or the second time or the third time. We need to be able to quickly launch some data flow job that will run a bunch of transformations and then produce an output, and then we need to check the output. And so we'll have to do this hundreds of times, probably more than that. And each run is potentially kind of slow because it's using a lot of different data. You don't want to parse all this resources and print them and deal with this. So you do need efficient encoding. In addition, so one of the things that we saw earlier about the Protobuf representation is that it generates code for you, right? And so this means that you get type checking. And again, this is sort of, some people like this, some people don't. But as your code base grows, this type of stuff is actually quite helpful and quite important. And it certainly has helped us out a lot of ways. And so this was never really a choice inside of Google. There's never something that we really thought about, like, what are we going to do? Everyone immediately came to the same conclusion. And the same thing with other teams across Google, like Cloud and DeepMind and Verily and everyone who works with this data, everyone sort of immediately comes to the same conclusion that we need some sort of Protobuf representation. It's just the obvious way that things are done in Google. So I realized that we are kind of a little bit in a bubble because Google has this immensely powerful set of tools. Like, for example, I was talking yesterday to someone and mentioned that if you have a file that is essentially encoding protocol buffer instances and you just save that file to the distributed file system, you can immediately run SQL queries on it. You don't have to do anything else, right? That file is in and of itself automatically available for SQL queries, all of them, for all data. And so, like, why would you not do it, right? For JSON, you can still run queries. It's a little trickier, whatever. They might be slower because there's parsing. It's not as optimized. But there are things like that that just made it an obvious thing. Also, Protobuf really dates back to 2001, right? It's a really mature technology. It wasn't open source until, I think, 2008. And there are some alternatives outside of Google, which makes it a little bit more nuanced. And it also depends on what you're actually going to do with FHIR data, whether or not this is like something that's suitable for you. And also I should mention that if anything, this looks similar to some of the reference implementations. Like if you did something in protocol buffer and FHIR, it would have a similar use as a reference implementation like Happy, for example, right? Because essentially it is encoding the FHIR data model in a way that you can use it easily from code. And so let me talk a little bit more about what FHIR actually would look like and what our approach was. So I'll go back and sort of talk about a little bit of historical context, right? So we started first looking at FHIR, I think about 3 years ago, and we weren't sure if it was the right thing or not. And so one of the interns actually that year started manually writing protocol buffer code or protocol buffer definitions for some of the resources like observation and patient that we thought we'd try out first. And then, as you might imagine, that pretty quickly becomes untenable. And also you'll make mistakes, right? There'll be some typo somewhere. And so we pretty quickly realized we have to actually go and auto-generate these things. And so we started doing that. And so that means parsing the structure definitions and really understanding all the nuances there. And there's quite a lot of interesting things inside the structure definitions, I think. If you're interested, I have a lot of things to say about that, but I think most of this crowd may not be as interested in that particular part, so I'll pass for now. And then it was also important to us that we had no interest in sort of forking the standard, right? So I think there's value in some binary format serialization like protocol buffer in the standard, but it's not something that we take lightly. And so we took care to essentially see this as an internal, really internal tools that help us work with FHIR data. But when we talk to external servers, we still use the standard FHIR JSON format. So that makes it sort of transparent whether or not you're using protocol buffer or not. And then another thing that is really a sort of a protocol buffer kind of mindset that we have is you want to do as much parsing as possible when you move data into the protocol buffer, right? And so this may include things like splitting strings or parsing dates or stuff like that, where if you don't do it early, then the code will just come up over and over and over again across your code base, right? So you'll have, hundreds of thousands of times where For example, you're parsing the date in a string just because you want the timestamp, because everything else in your code base, every library wants timestamps and not ISO formatted date strings. And so we do that up front when possible. And then the other thing that we realized as we started out, FHIR is an immense spec, right? There's a lot in there. And when you start, it's hard to know exactly where to start. And you probably will make some mistakes about which strings are allowed in which places, like encounter.class, what is it allowed to have, which values is it allowed to have, or like gender, should it be male, or just like capital M, is that okay? And so things like that, you don't necessarily know when you start out. And so another thing that we try to do is where there are really strict things in the spec that we can enforce at a programmatic level, at compile time level, we try to do that, right? So for example, the patient gender, really there's only a few values that are allowed, so we'll make that an enum, and you can't set anything else for that field in the protocol buffer. So you cannot make a mistake, basically, when that's possible. And sometimes it's not. Like language, for example, there is not really a closed set of languages that's available. And so you have to leave that as a string, and someone could potentially make a mistake and put something there that's not. All right. And then also the parser obviously enforces more constraints at runtime. And we also wanted to support the entire spec, because we realized as our usage grew that we can never quite predict what would come next, and it was just easier to just do it once and make sure that have we covered everything. And we also wanted to cover things like profiles and extensions in detail, and I'll talk a little bit more about that later, because that actually makes the use of FHIR easier. And as I mentioned, when we can, we decided to inline value sets. Right, so let's look at an actual FHIR protocol buffer method. So this is part of the GitHub repo, so the patient resource. And so we have a couple of protocol-specific things here. So the option that you see up there, for example, is it's used by the parser to do certain things differently. But comparing to the sort of resource on the right, which you can see is just an excerpt from the FHIR website, we essentially take the same fields and the comments from the fields, and they appear in the protocol buffer as comments there, and then the tag numbers are automatically assigned. And we've decided, so in the cases where there's a patient, which is a domain resource, or which is a resource, we're just going to flatten all of that. And we did it a little bit differently in the beginning, and this is better. And so we have this special field called contain resource. So as you know, any resource can contain any other resource, which is a little bit, it's very flexible. It's a nice thing in the spec, but it makes certain other things complicated, right? For example, the JSON representation, because of this, the raw full JSON representation is almost impossible to load into a database for this reason, right? Because it isn't a strictly defined schema. Like the resource could be any of many different things, so you can't fully design a schema for that. And similarly here, because every resource can include every other resource, it turns out they all have to appear in the same file in order for this to resolve. And so the actual main file that contains all the resources, resources.proto, is 17,000 lines. And so for comparison, the most complicated protocol buffer that we have internally, which is a web search related one, is about half that size. So that's sort of the complexity of healthcare data. Right. And then I'm going to talk a little bit more about extensions later. But you can see here that we have things like human name actually is its own type. And so all the data types essentially are defined out contact point. And here again, administrative gender, which is the gender code. And here's what that looks like in practice, right? So it's auto-generated from this specific value set. And it contains as an option, which means these things, the strings are available to things like the parser that can validate various things, but they're not actually going to be serialized on disk and not take up space on disk. Right. And so here's an example of what it might look like to actually interact with this. So on the left-hand side, you see the JSON, the sort of normal patient JSON for a very, abbreviated patient. And so in Python, what it might look like to create this thing in code is shown on the right? So you can see that essentially it's pretty straightforward stuff, maybe with the exception of how you add things to repeated fields, but even that is actually not that complicated to wrap your heads around. And so this is what it would look like in sort of the ASCII, the text version of a protocol buffer representation. So everything here that's not in quotes is not going to be a string on the wire, right? So the ID, right, is essentially going to have some tag number like 1, right? So when this is serialized, it'll be like a 1. That's just 1 byte. Active will be some other byte. And so it's actually quite compact. And I think on average, when we look at the data, it's about a factor of 10 smaller than something like the JSON representation, which obviously make a difference when you're dealing with tens or hundreds of gigabytes of data, or even terabytes of data sometimes. And I also want to talk a little bit about the primitive types and how we actually generate those. So again, there's numerous fine details that go into like how we actually generated it and what decisions we made for generating just this type of protocol buffer. And it was a lot of discussions with Graham and Ewart and James Agnew and others. And so those were quite helpful. And here, this kind of highlights one of the things that Graham mentioned earlier also about the JSON representation of data, right? So there's this thing called extensions on primitive fields, right? And so you could have a string that has an extension, and the extension might be something like a translation. And if you want to support the entire spec, you need to support this. In JSON, normally you don't have this, and you just have name and then the string, right? But sometimes you have underscore name, and that really means that is the extension on that field. And so they're two separate fields, and it's kind of hard to work with them being separate. So in the protocol buffer representation, we actually combine these. And one of the drawbacks of that is that now you have this bool here, like this value inside the thing, which is the main value. So a lot of the time you do have to, depending on where in the code you are, sometimes it's enough to pass the types around. But sometimes you have to add this extra dot value to actually get to the value that you want, which is a little bit unfortunate, but is better, I think, than the alternatives. And so here's decimal. So it's pretty much the same as Boolean, but the primitive value is of a different type. And so we're using string to encode the decimal. And the main reason really for this is what Graham wants. And he's kind of right, because in order to preserve the precision of decimals, it's just harder to do it with a double, right? You can't just do it with a double. If you had a double, then you also need some sort of other indicator of what the precision was, and that just gets complicated, especially to parse it, and you have to do the parsing in different languages, and then, yeah. So this is one of the few cases where we went sort of against the normal convention, right, to essentially leave the raw value. Because it's possible here, technically, to put a string that's not a decimal in there, right? And so, whereas a double is a double, right? So you can't make that type of mistake. Similar with datetime, the time types, I'm just going to show this one. Here, we actually parse each date into essentially the timestamp since the epoch in UTC. And so that's what the internal representation is. We keep the time zone and we keep the precision. And so we've tested this on all the examples on the FHIR spec website, where we can convert things back and forth without losing any precision whatsoever. But a lot of times in code, it's easier to use this timestamp type representation. In fact, almost always for us, it's easier. The only exception is when you display it to the user, but you already have code to turn this blob into a string, and so that isn't a problem. And I want to talk a little bit about an extension here, and so I picked one that's like a medium complexity, not the smallest and also not the largest, and it's patient nationality, right? So when I say it's not the smallest, not the largest, it has two fields, right? So there's the easiest extensions have just one field. And then you can imagine, it's a codable concept. It's simple. You can imagine just sticking it in the original definition. But if you have multiple fields in an extension, what actually happens in the FHIR spec is it gets expanded out like this, right? And so you can see that, let's see, actually on the next page, hold on. I'll get to an actual example of what this looks like in JSON, but at a high level, right, there's this nested structure that actually is quite complicated to work with. I don't know if anyone's ever really done that for some of the trickier extensions, but it gets very cumbersome very quickly. There's lots of loops, you're checking for things, or maybe you make some sort of hash map, or maybe you have some code that does it for you, but it's doesn't quite fit in the overall thing. And so what we've done here also is we can generate extensions from structured definitions as well. And so here we just collapse them, and it looks kind of like a normal resource would look, right? So you just have a codable concept and a period here. These are the two fields in this extension, right? And so in addition to that, so this is not quite out in the open source version yet, but it's something that we're playing around with and will eventually get out. You can imagine that if you have a profile for a patient, for example, that has nationality in there, when you generate the protos, and so I should mention that these protos, we have a version that's generated from the base spec, but you can generate your own protos from other profiles if you want. And so in particular, it might be convenient to take one of these packages of implementation guides and generate just the protos that correspond to those resources, which might not be then 17,000 lines, right? Because now you don't have vision prescription, for example, because you didn't need it, right? And you just have the 18 or 20 or so resources that you care about. And in addition, maybe there's some extensions that you care about, right? And you don't want to deal with the .NIC extension and all that stuff. So if you specify them in the profile, they should be inline like this, right? And so what looks like in the JSON format, again, this is an even more abbreviated picture. This basically is just the extension, except for, I guess, the gender, right? And so let's say you wanted to put in an extension that's nationality and just the code, not even the period, right? So one thing, it would look like this, right? Where you have essentially extension, and then it specifies which extension, and in that there's another extension that specifies which field of the extension, and then in that there's the value, right? And so you have this very deeply nested, complicated structure. If you do the proto version and you've inlined it in the way that I showed in the earlier slide, in order to get to this, you can actually just use this like you would any normal field in the FHIR spec, right? To just say, I've defined it as nationality, so I do patient.nationality.code, right? And then I can just do that. And when this gets serialized to JSON, no one is the wiser that this is what you did, right? When you send it over the wire to someone who is not using the protobuf representation, they will be able to deal with it in the same way they were dealing with it before. But as you've, I think, picked up here, right, so the JSON, so protobuf comes with a JSON representation, but is not the same as the native FHIR JSON representation. So the one major thing that has to be done for each language that is supported, each language which is going to interact with the outside world, I should say, has to have a FHIR JSON parser, right? So right now, only Java is in the open source version. We have C++ and Go implementations internally, and the Python implementation is on the way. And we are just untangling some internal dependencies in order to get this ready to open source. But it's definitely coming. And if other people want to contribute, this, I think, it would be for other languages, the most important contribution that you could make. Okay. Let's see. All right, so let me talk a little bit more about what we already open sourced and what's coming. So it's still early days. So the version 0.1, as we call it, we released in March. And so basically it has all the STU3 protos. It contains things like it has things like contained resources, extensions, and the enums. It has the JSON Java parser. And it had one example, which is generating Cynthia data and uploading it to BigQuery so that you can run some of these queries like y'all showed in the demo on that data. And if you have your own data, right? You don't need obviously the Cynthia data. You can just use the same example to upload your own data to BigQuery. It's actually fairly easy to set up a BigQuery account. So this is something that if you're interested in running queries, I would recommend trying it. And again, if you have feedback of what works well and what doesn't, let us know. I should mention this is STU3 only. We probably will at some point, we'll definitely do R4, and we'll probably at some point also do DSTU2. But again, this depends on what you guys want. Internally, we're all switched to STU3 now. All right, and so version 0.2, I realize we haven't actually put this tag on the repo, but this is the current thing that's out there today. And so the main difference there is now we included the entire code to auto-generate protos. And so there's an example of how you auto-generate the spec from, auto-generate the default protos from the spec. And then also we've worked with the Argonaut and other people on the bulk download. And so we tried this in the Connectathon in Cologne last week. And so there's an example that works with the current version of the bulk download spec, where you can essentially, it's a client that you can point to any bulk download capable server, and it will pull down the data and, again, upload it to BigQuery if you want. And we actually found some interesting, we found some bugs in various FHIR implementations of various vendors as we tried this in Cologne. Partly because, there were, for example, there are like strange edge cases, like, well, not strange edge cases, but maybe not the things that you would test. Like, for example, the duration needs to be, in some field, needs to be of a type units of measure, and year is like A instead of year, or something like that. And there was some vendor that didn't have that right. And so when we parse into Proto, it just complains and says, this is not right? And so you get a bunch of simple validation there that even fairly sophisticated people might actually miss. So that was interesting. And then I want to talk a little bit about what's coming next. So I was hoping we'd have this done by now, but it's almost done. It's almost done. So if you think back to the earlier slide where we had this bucket that went from the FHIR to the TensorFlow, that's essentially what's coming in version 0.3. And so this includes things like converting your data to TensorFlow features, and also some tools to help you put labels on your data. So really with the features and the labels, you have all the pieces that you need to start training some models. There's obviously a lot of work in designing those models as well. And so we'll open source some, and I expect that the community in general will quickly start contributing more. All right. And so the goal here that we want to get to really is we want to make it as easy to do machine learning on healthcare data as it is today to do it in computer vision, right? And so I actually have a background in computer vision, and a decade or so ago, nothing really worked, right? And at some point, deep learning just got good enough, and now you can, I know, small startups that decide one day that they're going to add machine learning to some images in their product, and they know nothing about TensorFlow, and they download some open source tutorial, and they try it, and 2 days later in their product they have something that is able to classify images as bedroom or view or something like that, right? And there's no reason that shouldn't be available in healthcare as well. Like if you have an app that tracks glucose or things like that, maybe you want to make predictions about what's about to happen before you actually see it happening. And so you should be able to just try that out. You should be able to add some labels, train some models, and see how you can use that to help your app. And so again, here's sort of the view of how, so this is coming in the next version, how the features really are all the resources in the FHIR spec that you put in there. And that's really what is going to power the model. And so finally, again, how do I use it? Well, you download, you try, and you give us feedback. All right, I think we're out of time. So thanks guys for coming.